Our next presenter is SCFCan, Christiane Street and Russ Stiver with SCFCan. They're going to tell us about their supercritical fluids and how they extract out of drilling waste and recycle drilling fluids and oils and keep that from going to a landfill. Hopefully, welcome Christiane and Russ.
All right. Thank you, Dan. Hello, everyone, and thank you. Yes, we are SCFCan. I'm Christiane Street, and I'm joined by Russ Stiver, our financial officer. Today, Russ and I are going to talk about SCFCan's technology, and in particular, our process for recovering lubricant oil from drilling waste using supercritical fluids. So today, I'll be speaking to SCFCan's corporate vision, our technology as it applies to drilling waste, the environmental performance of that technology, and then I'll pass it off to Russ to speak to our business models. So SCFCan's corporate vision is to become a leader in the circular economy by using our supercritical fluid extraction technology in the recovery of valuable compounds from waste streams, such as drilling waste. In doing so, we'll be shifting a waste to a resource while providing an economic win for everybody involved, meanwhile driving significant life cycle greenhouse gas reductions. I imagine quite a few of the viewers today are comfortable with the concept of drilling waste, but if not, these are the basics that you need to know. So drilling oil and gas wells generates an oil contaminated waste, and quite a bit of it. A typical well would produce around 500 tons of waste containing around 500 barrels of lubricant oil. The lubricant oil has a value, is a highly refined product, so has a value of around 35,000 US in the waste of a typical well. Unfortunately, quite commonly, this waste is sent for direct disposal in landfills with no further treatment. So in addition to the loss to the drilling operator of the oil and the waste, they also have to pay landfill tipping fees. And then once in the landfill, the oil is degrading and forming methane, which isn't great from a greenhouse gas point of view. So SCFCan's technology uses carbon dioxide as a supercritical fluid. So CO2 at high pressure, above about 7 megapascals, and at moderate temperature, so anywhere above about 30 degrees Celsius, it becomes a supercritical fluid, which is simply another state of matter, but like liquid or gas, but supercritical fluids have very favorable solvent properties. And the figure that we have here is a relationship between the solubility of a common drilling fluid, oil, with relation to pressure and temperature of the operating process. And as you can see, it has a pretty strong relationship with pressure, which is the bottom forward axis, and solubility being the vertical axis. And we exploit this solubility curve in our technology. So we operate our extraction vessel at high pressure. So this would be the high solubility region. And this is where we're extracting the oil from the waste into the CO2. Later on, in our separation vessel, we operate at a lower pressure, and therefore we're in the low solubility region, and the oil drops out so that we can collect it. Our technology has a low energy recirculation cycle, and carbon dioxide is considered safe, inert, and environmentally friendly or green when you compare it to liquid solvents, common liquid solvents. I'd like to just show a quick video that explains a little bit more about our extraction process.
The pilot scale fully continuous supercritical fluid extraction process. Two main loops exist within the process. The feed loop, shown in green, and the CO2 loop, shown in blue. The feed loop starts from the slurried drilling waste feed tank. The slurry flows into a positive displacement pump, where it is pressurized and sent to the top of the extraction vessel. The core of the process is the extraction vessel. It operates at high pressure and modest temperature. Here, the slurried waste flows from top to bottom. The oil is removed from the drilling waste and transferred into the supercritical CO2. the end of this loop, the clean slurry flow exits from the bottom of the extraction vessel and is piped to the treated waste tank. The CO2 loop starts from the CO2 feed tank. A positive displacement CO2 pump delivers the CO2 feed to the bottom of the extraction vessel, where it flows up to the top. The CO2 and slurry flow are countercurrent. While the CO2 flows to the top, it extracts the oil. The CO2 and oil leave the top of the extraction vessel and move on to the separator. The separator is at a lower pressure and temperature compared to the extraction vessel. As a result, the oil condenses out and is collected at the bottom of the separator. The liquid oil can be removed continuously or intermittently from the separator. At the end of this loop, the oil-free CO2 exits the separator, and in commercial applications, it is recycled in the process. The whole system is controlled automatically for safety as well as process stability and performance reasons.
So, to summarize the key points from the video, we have our two loops, the waste feed and the carbon dioxide. They meet in the extraction vessel under high pressure. So again, this is the high solubility region where the oil is extracted from the waste and enters the CO2. The CO2 and oil then flow to the separator. Again, this is the lower pressure side where the oil is dropped out and collected. What really sets SCFCan's technology apart from other industrial supercritical processes is that we are fully continuous. So we have a continuous feed and removal, which eliminates lost time to fill and empty like you would see with a batch process. Our extractor operates in countercurrent flow, so we have a contact time of minutes rather than hours. And ultimately what this equates to is lower capital and operating costs. In terms of drilling waste, this is what we see. We have a raw drilling waste, which we process with our technology, and we get out the virgin quality extracted lubricant oil and the clean solids. In terms of environmental performance, those clean solids contain less than 1% of the lubricant oil. And what that does is open up the potential for reuse of those clean solids in other applications. And if you compare our process with virgin lubricant oil production and landfilling, our process offers a 75% reduction in greenhouse gas, life cycle greenhouse gas emissions. I'll now pass it over to Russ to speak to our business model.
Thank you, Christiane. In commercializing this technology, we can either take the waste to the technology, or we can take the technology to the waste. These two models are not mutually exclusive. They can be pursued simultaneously in different regions of the world. In terms of taking the waste to the technology, that would be a regional facility, and there are scale advantages there because the process is fully automated. It doesn't take much additional labor to double or triple capacity. In taking the technology to the waste at a mobile drill site, here you'd have the extraction and recovery units right next to the drill rig, and it provides a tight reuse loop, which allows real integration with the driller, which creates some cost advantages in that respect. This next slide illustrates the economics of our process. You notice two things on the slide. First is that our total cash operating costs are below $40 per barrel, regardless of whether it's the regional or the drill site version. And there's really two components to our costs: labor and utilities. There's not much else to this process other than those two things. Second thing you'll notice is the significant margin or gap between the cash costs that we have and the value of the lubricant oil that we recover, even in the current environment in which lubricant prices are depressed due to the COVID epidemic. We still have a significant margin of profit, which is key because it's this margin that allows us to change the dynamic from one in which industry is asked to subsidize environmental technologies to one in which there's a profit incentive, and we can incentivize drillers to work with us to clean up the environment, provide a profit motive to them, and also provide a great return to our investors. In terms of the capital costs to build a facility for a regional facility, it's around, well, it's slightly less than $65 per barrel of capacity, which relative to the cash operating margin we had of could be $35 to $55, $60 per barrel. It's quite attractive. You're looking at, less than a 2-year payback. For a mobile unit, it's about $100 per barrel of capacity. The capacities of each of these different operating models, regional facility, there's really no limit to it. It's really limited by the number of drilling rigs operating in the area within, we think, about a 200-kilometer radius that are willing to send us their waste. For a mobile unit, this is sized to absorb the waste produced by a single drilling rig, which is around 13,000 barrels of oil recovered annually. Despite the attractive margins, we still think there's upside from there. Several different areas of upsides. Carbon credits, the rules vary by jurisdiction, but carbon credits are designed to encourage and incentivize the introduction of technologies that reduce greenhouse gases, and that's really what we do. So we expect to be eligible for carbon credits. Residual solids reuses, once we've extracted the oil and produced clean solids, we don't think there's a really strong reason why those need to go in a landfill, and we'll be pursuing alternative uses of those. There's a number that come to mind, cement manufacturing, road construction, there's several things along those lines that those solids could be used for and not go into the landfill. There's obviously upside in lubricant prices from where we are today, which will provide additional profits. Heat and electricity integration. We've been very conservative in our modeling in terms of how much waste heat we recover. We think there's certainly a lot of upside there in terms of integrating and getting that waste heat and using that to heat the slurry going into the extraction vessel. Labor integration, particularly at the well site, if we're right next to the rig operator, we can integrate labor with them because the process is really automated. We can use their labor to operate the equipment and cut costs significantly in labor. There's also scale economies in capital costs. The first one you build is always the most expensive, and it goes down from there. So we expect the cost of building them to drop over time. How do we get there from here? The upfront investment to build a system is about $3 million. That will cover final design, capital construction, and startup losses. There's potential for a portion of this to be covered by government grants. We've had preliminary discussions with some government grantors, and we're optimistic. This $3 million will produce an initial field facility or unit, be designed, built on site within 18 months. Starting, training, troubleshooting, ramping up to capacity will take about 6 months. And at that point, you have a unit that is free cash positive, which means that those cash funds generated can then be used to either expand capacity in the case of a regional facility or to build another mobile unit if we're doing the mobile model. I'll now pass it back to Christiane for a summary.
Thanks, Russ. So in summary, using SCFCan's supercritical fluid extraction technology, there's a sizable opportunity here for both an economic and an environmental win. We've shown we can recover the lubricant oil for less than $40 a barrel and cut life cycle greenhouse gas emissions by 75%. And in concrete terms, if we applied our technology to 2,400 wells being drilled, we'd be able to reduce greenhouse gas emissions by 1 megaton and recover 1.2 million barrels of lubricant oil that has a value of around $80 million US. So again, a very sizable economic and environmental win with SCFCan's technology. Thank you kindly for tuning into our presentation today.